Okay, so here we have a hydrostatic force problem. So a vertical dam, looks more like a rectangle to me, semicircular gate, find the hydrostatic force against the gate. Okay, so it says 12 meters tall. There's only 10 meters of water in there, so useless information. 4-meter diameter gate means it's got a 2-meter radius. That's important. Okay, let's go to the old light over here. Okay, so we're going to use this formula here. Hydrostatic force equals density of the water, times gravity, times the depth, times the area of each individual little slice that I'm going to show you in a sec. Good. Okay, so the density of the water is 1,000 kilograms per meter cubed, I believe, and then the rate of, gravity is 9.8 meters per second squared, and the depth is, we're going to find that out in a sec. Right. Okay, so here's this. You're going to label this, this is going to be X values. Right. So your depth is going to be not this. This is wrong. It's going to be depth equals 10 minus X, because this is your overall here, and you're going to label it starting at the top at 0, down here is going to be 10, so it's going to be upside down. So down here, let's say it's got a 2-meter radius, so like at the top here, you're at 8 meters down, so 10 minus 8 is 2. Oh, I see, did this backwards. Okay, yeah, label it 10 at the top to 0 at the bottom. This is why it's important to check your work. Now, if you say you're at 2, then you say 10 minus 2, and that means your depth is 8, because you're 8 meters down in this tank. Alright, so, yes, 10 minus 8 was right, but label your 10 up here if you use this as your depth notation, and 0 down there. I was getting it confused with, where'd it go? This one, where you're pumping water out, and it's easier to label your bounds upside down like this, with 0 at the top and the height of the tank at the bottom, but not this problem. Alrighty then. So that's your depth, and then we'll plug that into the equation in a second. Now we got to find the area. What we're going to do is we're going to blow up that gate. Not with like dynamite or anything. There. So there's our gate with our 4-meter diameter and our 2-meter radius. And so what we do with this is the area equals length times width. Right. So we're going to chop this up into little slices, and we're going to take the area of each of these slices, because this is a gate. It's not three-dimensional like the tank is. It's pushed up against the front glass. Well, it's a dam, but if you think of it as a tank, it's a little easier to conceptualize. Like, here's the tank wall, and there's the plate, or the gate here. This is from a side view, so it's flat. Anyways, you're going to take the area of one of these little slivers of the gate. The height is delta x, because it's the change in x, because we labeled this top to bottom x values here. So the height of the gate is going to be delta x. And the length of the gate, this is fun. Well, you can pick any of these to find a formula to get the length. So just draw your radius line out here. This is going to be 2, and this line here is going to be x. Yeah, you can use x. It's cool to use x because 0 is on the bottom, and so is this is touching the bottom. So you just, the height of this x value is, well, it just works. Never mind. Okay, so just use x for this. Then you use Pythagorean theorem. You get the square root of 4 minus x squared equals this. But it's only half of the length of this particular segment that we're finding. So you have to multiply it by 2. Why did I draw this line here? Where did that come from? So the width of any one of these given little slivers here, or the length, and this is the height, the length of any one of these given slivers here is going to be 2 times square root 4 minus x squared. There, so your area is going to be that times delta x, length times width, or length times height, I guess in this case. Dimensions suck. Okay. Now we're going to plug everything into our equation. So we've got P, G, D. I'm going to use parentheses. Remember, our depth, D, was equal to 10 minus x times our area, 2 times square root of 4 minus x, delta x. Alright, then guess what? We turn this into an integral because this is calculus, and everything is an integral. You can pull these constants out here. So that's going to be 9,800. Say from what are our bounds? Give me a second. I'm not gonna make another video. I refuse to make another video. 0 to h, or 0 to x. So yeah, so 0 to x, your maximum x value on the thing you're finding the hydrostatic force on is 2. So 0 to 2. Then, alright, so then just fill in the rest of these holes here. You could probably pull that 2 out, couldn't you? Yeah, you could pull the 2 out. Just 2 times, pull that 2 out there. Square root of 4 minus x squared dx. Cool. And then you just do that thing there. What would that be? It'd be 19,600. Yeah, 19,600 maybe. I don't know. And then you just integrate this, which I'm not going to do. Use Wolfram Alpha or something. Anyways, your final answer will be that. Okay.